we're factoring, we're looking to take polynomials and change them from a series of terms into a series of factors, so pieces that are multiplied together. If a polynomial is prime, we can't do this. Remember that a prime number is divisible only by plus or minus 1 and by plus or minus itself. So a prime polynomial is only divisible by plus or minus 1 or plus or minus itself. We'll see what this looks like. It's not nearly as complicated as I think this first definition can make it sound. What's important is that factoring is the opposite of expanding. So it's the opposite of what we were doing, for example, in algebra basics. We'll see a couple examples of this. We'll start with common factoring. Two reasons for this. It's probably the most straightforward. It's probably the most useful. Actually, I'll give you a third reason. It's the one that we're going to look for first with every type of factoring problem that we tackle. Okay, so we're asked to find the greatest common factor in each of these expressions. It also says to factor completely, which means that any patterns that we see, we should factor. For these four, the only thing we'll be able to do is find the greatest common factor. Factoring questions are easy to check because we're actually better at starting with the answer and going back to the question. And we'll have a look at that. I'll start out quite formally. So we'll go in great detail and then I'll start to speed up the process. So let's look at 12x plus 6x squared. What are the common factors in those two terms? Well, in order to answer that question, we have to be comfortable with knowing what the factors are. Generally, when we talk about terms and factors, we'd say, okay, this is we have a major term, 12x, and another major term, 6x squared. And then we would talk about the major factors, 12 and x for the first term and 6 and x squared for the second term. But this is one of those places where knowing what the prime factors are is really helpful. So what are the prime factors of each? This is where our factor trees come in useful as well. So the prime factors of 12. Well, let's throw out some factors of 12 first. 4 times 3 is 12. Pick any two. You could use 6 and 2. You'll get to the same answer. 3 is prime. So 3 is a prime factor of 12. But 4 is the product of 2 times 2. Both are prime. So the prime factors of 12 are 2, 2, and 3. So I'll write these underneath. 2, 2, and 3. And of course, there's an x there as well. So the prime factors for the first term are 2, 2, 3, and x. Prime factors for the second term, well, 6 is divisible only by 2 and 3, and both are prime. And x is divisible by x times x. You don't need to do this, and if you already see the answer, it's not a problem to go ahead and write it down. But this can help us when our problems get a little bit more challenging. What factors do they have in common? Well, both are divisible by 2. Only 12 is divisible by a second 2, so that's not a common factor. But I see that both are divisible by 3, and further, both are divisible by a single x. 6x squared is divisible by a second x, but the first term isn't. So what is the greatest common factor? And you'll see greatest common factor written often as GCF. Well, the greatest common factor here is 2 times 3 times x, or 6x. Okay, so we write down the greatest common factor first because that's what I'm going to remove from both the 12x and the 6x squared. So what do I mean by removing? I mean I'm going to divide out the prime or the greatest common factor. So I'll take my 12x and divide it by 6x. 12x divided by 6x, in other words, 12x divided by 6x is 2. So when I take 6x out of 12x, I have 2 left behind. When I take 6x squared and I divide out 6x, in other words, when I take 6x squared and I divide out 6x, what's left? Just an x. So 2 plus x. You can also look at it this way. There's a 2 that was unique in the first term and an x that was unique in the second term. And we find that that's what's left in our brackets. All right, what do I mean that it's really easy to check? This is our final answer. But how do I know that it is correct? Well, I'm going to use distributive property and get right back to the previous. What is 6x times 2? Well, that's just 12x. And what is 6x times x? Well, that's just 6x squared. So these are, in fact, equal. This equal sign here isn't a liar, and I factored it correctly. Remember, I've got two terms in this case in the question, and in the answer, in the factored version, how many terms do I have? Just the one. I have 6 times x times bracket. So this is the final factored form. I encourage you to pause the video and try the next question. 6x cubed minus 20x plus 4x squared. I'll tackle this one in much the same way as well, that we'll work through the prime factors, make sure we know what the GCF, the greatest common factor, is, and go from there. Maybe you're just looking at 6, 20, and 4, and you're immediately pulling out what the greatest factor is, and that's fine. I'll catch up to you. Factors of 6x cubed are 2, 3, and x, and x. The factors for negative 20x, I'm going to separate the negative one to highlight it. And the prime factors for 20, well, maybe we'll do a quick factor tree. 10 times 2 is 20, 2 is prime. 5 times 2 is 10. So the prime factors for 20 are 2, 2, and 5. So for negative 20x, I have negative 1 times 2 times 2 times 5, and then times x. And for 4x squared, I'll write down 2, 2, x, and x. What's the greatest common factor? Let's look at what they have in common. All are divisible by a 2. So now that I have 3 terms, I do have to be able to circle that factor in each term for it to be common. And I'm out. That's all the numbers. Let's look at the x's. I can circle an x in each one. So it turns out that the greatest common factor is 2x. So I'm going to write the greatest common factor down. Because these expressions have to be equal, the question and the answer, I can't just take the greatest common factor and throw it away. It's a really common error to find the greatest common factor and then omit it from the answer. You do have to make sure that it's there. Also, if I have 2 terms in the question, you notice that I had 2 terms in the brackets for the first question. Here we have 3 terms in the original expression. So inside the brackets, I will also need 3 terms as I pull a 2x out of each one. So 6x cubed divided by 2x is 3x squared. What I also notice is that I have a 3 and 2 x's left once I've circled and removed by dividing out the greatest common factor. So this is a nice way to see what's left over as well. In the second term, I have negative 1 times 2 times 5, so we have negative 10. And in the third, 2 times x, so plus 2x. And that's our final answer. You can check it using the distributive property. Let's try one more. Can you see this one without writing out the prime factors? First, I'm going to look at the numbers, 3, 6, and 12. What's the largest factor that goes into each? The largest factor of each? Well, 3. I can't pull out a larger number from the 3ab squared, so that's going to have to do. Now I'll look at the a's. Look at one of the variables. Each one does have an a, so it has a greatest common factor that has to include an a, and each one has a b. How many b's can I pull out? Well, I can only pull out 1 because that's limited by the middle term. I can't pull out 3 b's because I can't take more b's than I've got. So the greatest common factor here is 3ab. What's left? I have a 3ab squared, and I've pulled out the 3, the a, and the b by dividing them out, so there's a b left behind. Negative 6ab divided by 3ab is just negative 2, and 12ab cubed divided by 3ab is just 4b squared. Sometimes a good idea to look at the answer and see if there's anything left in the 3 terms in the brackets that I could have taken out. And if I've forgotten to take it out, I simply do it in another line. It's not a problem. Do a quick check using distributive property to make sure you can get back to the beginning, but don't actually expand it. because we do want the answer as the factored form. We're just using that as a check. Okay? I threw this last one in because that's a lot of negative signs. So usually, if we've got some negative signs, if we've got negatives in each term, then we'll pull that out in the greatest common factor. But what we're going to see later on is that even if not all of the terms are negative, frankly, even if none of the terms are negative, we can always factor out a negative one. So let's keep that in mind. But in this case, having three terms that have negatives, first of all, it is certainly common to all three. And second of all, we prefer writing plus signs. So we are going to pull that out so that we minimize the number of negative signs in our expression. Quite quickly, let's write down the prime factors for this one again. So we have negative 2, 2, 2. Sorry, negative 1, 2, and 2. There are 3 s's and 1 t. For the second term, we have negative 1. And we've already factored 20. We know that the prime factors are 2, 2, and 5. We have an s and we have a t. And for the final one, I've got negative 1. Okay, 18, if I draw a quick factor tree, maybe you've done 6 times 3, maybe 9 times 2, we'll get to the same answer. The prime factors are 2, 3, and 3. So negative 1, 2, 3, 3, t, and t. What do they have in common? Well, they certainly have the negative 1, but I can always divide by negative 1 if necessary. They have a single 2. That's it. I don't have a second 2. Do I have a single s? Oh, I should not have circled that because I only have s's in the first term and in the second term, not in the third term. So those are not common factors to all three, but I do notice that each of them has a t. Great. We found the greatest common factor. Write it down. Keep it in your answer. Don't chuck it out the window. So it is negative 2t. And what are the 3 terms remaining? Well, I've got 2 times s times s times s. So that's 2s cubed. Again, that's what I get when I take negative 4s cubed t divided by negative 2t. For the second term, I've got positive 10s and then positive 9t. They have nothing else in common, some even numbers, an odd number, some s's, a single t, and we're done. And what I mean by minimizing the number of negative signs, instead of having 3 terms with the negative sign, we have, well, we only have 1 term in the answer. There's a single negative, and the terms inside the bracket, inside this last factor, are all positive. These look a little bit trickier, but they're exactly the same. There's nothing different going on here. Again, the instruction is simply to factor completely, and that will be the instruction for each of these questions. So we have to decide what sort of factoring, what style is going to be most useful. Right now, we're only familiar with common factors, and that is the only thing we will be able to do for these ones. All right, what is the greatest common factor for this first example? 15, 3, and 10. Well, 15 is divisible by 3, 10 is divisible by 5, so is 15, but there's no number that goes into both 15, 3, and 10. They do not have any numbers in common. But they have some x's. I've got x squared, x to the power 4, and an x, so I can take out a single x. That's the largest number of x's I can extract. And 2 y's. So what's left? 15x squared y cubed divided by xy squared. So that's 15x squared y cubed divided by xy squared. Right? This is exactly what we were doing with exponents. And now we've essentially moved on from doing it on paper, writing it down, to doing it in our heads. We have 15 left over. X squared divided by x leaves us a single x in the numerator, and y cubed divided by y squared leaves us a single y in the numerator. The difference here is that we should always eliminate our denominator. If we've got a denominator suddenly, we didn't find the greatest common factor. We found a factor that was too large. 15xy. 3x to the power of 4, y squared divided by xy squared, or you can think of it as taking out an x and a y squared, leaves us with 3 times x cubed, and there are no y's left. And then finally we have minus 10. That's it. And we're done. This is one of those instances where you might be tempted to take out a negative 1. So it would be not incorrect, let's say, to take out a negative xy squared. And then look what happens on the inside. Check that that's correct. Negative times negative is positive. Negative times positive is negative. Negative times positive 10 is negative 10x squared, so that still works out. In this case, it turns a first term that was positive, which is fine, into a first term inside the brackets that's now negative, and we tend not to do that. And also by factoring out a negative here, we haven't really reduced the number of negative signs overall. So in this instance, for two reasons, because not every term explicitly has a negative 1, and because by pulling out a negative 1, we don't reduce the number of negative signs. We tend not to do it here. How do you know when it's useful? It'll depend on the larger context of this problem. All right, I like this next question over here because it looks hard, but it's so much easier than we think it is. If we go back to basics, how many terms are there in this expression? Big picture, major terms. Well, there are 2. When we look for the greatest common factor, we're asking ourselves what the factors are in each term and what they have in common. All right, maybe I'll just write out the major factors this time rather than the prime. We've got 8, y cubed, and 3x plus 4, but there are 7 of those multiplied together. Those are the major factors of the first term. The major factors of the second term are 24, y, and 3x plus 4, but there are 5 of them this time. What do those two have in common? Even without resorting to prime factors, I can tell that 8 and 24 are both divisible by 8. So 8 has to be part of the greatest common factor. There are 3 y's in the first term, 1 y in the second term, so there's a single y in the greatest common factor, and then there's a couple of 3x plus 4's. How many? I've got 7 in the first term, 5 in the second term, so I can pull 5 of them out. And I put some square brackets in just to be quite clear about what's left over. Okay, so I've got 8y cubed, 3x plus 4 to the power of 7, and I've taken out an 8 and a single y. Okay, so I have 2 y's left. And I've taken out 5 3x plus 4's, which means I have some left over. I've got 2 left over. So this is the leftover from the first term. What about the second term? I've got positive 24 divided by positive 8 will be positive 3. Y divided by y is 1. And 3x plus 5 all to the power of 5 divided by 3x plus 5 all to the power of 5 is also 1. So that's all that's left. So to write this without square brackets, it doesn't necessarily look like it came from our question. Not quite right there. But it's absolutely equivalent. And again, you can prove it to yourself by using the distributive property. Okay, one caveat here, I'm going to leave it. I'm going to leave this final answer as I've written it because 3x plus 4 to the power of 2, and then if I take all of that and multiply it by y squared, I'm not really simplifying anything. It looks much tighter if I leave it this way. But if I have, and you'll see this in other problems, if I have something simpler remaining in the brackets, let's say that once I've pulled out the greatest common factor, I have something like y plus 2 plus 3. Well, that I can simplify. What is y plus 2 plus 3? That would just be y plus 5. So rule of thumb is if it's really easy to make this look tidier, do it. But if it would involve FOIL or even a larger value here, so we have to FOIL several times, let's leave it in this form. So that's what I'm going to do here. And our final example, it's got some fractions. Don't overthink this one. What do they all have in common? They've all got a 4 in the denominator. So let's take that out. There's a 4 in the denominator. What else do they have in common? Do they all have x's? Nope, just the first two, but they do all have a y. The largest number of y's I can remove is 1. So you could write that as y over 4 or 1/4 y. They mean the same thing. And then what's left over? Think of removing the quarter. Well, you'd have 2 x's left and no y's because you pulled out a y as well. Does it work in the forwards direction? What is 1/4 y times x squared? Yeah, that's 1/4 times x squared times y. So we're good. Here we've got 7x squared y squared. I'm about to run into my end bracket. And then finally I have 3y. Wasn't nearly as bad as it looked, was it?